Hello everyone, welcome back to another video of Marin Maths. This is the first video after 3 weeks since my last post, and I do apologize for that because I was kind of busy, and because of all of these world events that have been happening for the past few weeks, I have not been in the mood to make any videos. But today I'm going to show you another example of how Feynman's integration technique works in a very non-trivial example. So, and of course, I wish that I hope that you're all safe home, okay, that the coronavirus is away from you, and hopefully you're following the guidelines, the CDC guidelines. And if you're if you have to work, hopefully you do it from home and you don't have to go out, because it can be dangerous. Anyhow, if you have it, well, I hope you get better, and make sure that you put masks on so that you don't get anybody else infected. And remember that coronavirus can spread in an exponential manner, so that's why you have to be careful. And yeah, anyways, suppose that for this example, the speed of a coronavirus particle is described by this graph, okay? So it will follow this path. Well, this is the curve for the velocity function. So the speed reaches a maximum at this point, right? But it will be described by the following function. So the speed v of t is described by the function, okay, t multiplied by the natural logarithm, okay, of t cubed plus 1 divided by t cubed, all of that divided by t cubed plus 1, okay? So that is the function that describes this, hypothetical speed of a coronavirus particle. And so we want to find what's the displacement of this particle. What is the net displacement from this point at t equals 0, from time t equals 0 seconds, until, whoever knows, until infinity, okay? So whenever the particle stops, or whenever it reaches, some host to infect. So in order to do that, if we have the velocity function, we know that the integral of the velocity function with respect to time is equal to our position function. So if we take the integral of the velocity function from 0 to infinity with respect to time on both sides, we can get our position function. And if we do the definite integral from 0 to infinity, we get the displacement from 0 to infinity. And so here is this very non-trivial integral. And in order to evaluate this integral, I'm going to do a two-part presentation. So this is part 1, okay, because it can be very long and tedious, but it's very interesting, very non-trivial. So the integral from 0 to infinity of t ln of t cubed plus 1 over t cubed divided by t cubed plus 1 dt. All right, so in order to do that, we're going to use Feynman's favorite technique of integration, which is a very useful case of Leibniz's differentiation under the integral sign. So what we can do here is that because we know that x of t will be integral from 0 to infinity of t natural log of t cubed plus 1, okay, divided by t cubed plus 1, all right. Oh, I'm sorry, this has a t cubed on the bottom, okay. All of that is divided by t cubed plus 1 dt. Then, by using Leibniz differentiation under the integral sign, we take the derivative of this. So basically, we go back to our velocity function, but in this case, we're not going to get rid of the integral. But first, in order to understand what's happening, we have to, you have to be very clever, and you have to have a very good calculus intuition in order to find out which part of this integrand you're going to take advantage of, so that when you differentiate, you get a very easy thing that you can integrate back again, and so you can evaluate this in a much easier way. But it's not as easy as you might think. So in order to use Leibniz's integration, we have to choose some part of this integrand as a parameter. So it's going to be another variable that we are going to use for our own purposes to integrate this function in such a way that it's easier, okay, to decompose and later on integrate it in terms of elementary functions. So I did not come up with this parameterization, so it's very difficult to find the right parameter. So when I first saw the problem and I tried it on my own, it took me several days, maybe several hours each day to figure out which is the right parameter. So it's not trivial, but let's see. So in order to make this integration easier, we're going to let our new function, we're going to call it I for integral. Okay, I of some parameter alpha, okay, that's going to be our parameter. And so we're going to introduce this parameter, okay, in a way that makes this thing easier to integrate. So over here we have the integral from 0 to infinity of t natural log of t cubed plus alpha. So here's where we're going to put our parameter. Alpha, all of this divided by t cubed, divided by t cubed plus 1 dt. Okay, so this is where the parameter alpha comes into play. And what's going to happen next is that if you pay attention, the previous function that we had is in terms of t, but now this function is in terms of alpha, which means that t in this case would be considered as a constant, right? So it's a two-variable function, okay, per se, and we have an integrally defined constant. So what comes next using Leibniz's integration, differentiation and the integral sign is we take the derivative on both sides with respect to alpha, okay? So if we take the derivative d over d alpha on both sides of this integral, we're going to get the following. Using Leibniz's differentiation and the integral sign, we can bring that differential term in the inside, and so we get something like this. We get that I prime of alpha, okay, is nothing but the integral from 0 to infinity of the partial derivative with respect to alpha of this function t times natural logarithm of t cubed plus alpha, okay, divided by t cubed. All of that over t cubed plus 1 dt. Okay? Now in this case we're going to take the derivative with respect to alpha, right? So what's going to happen here is, we're going to have some chain rule to do. But first let's expand this a little bit using natural logarithm properties. So we get nothing but the integral from 0 to infinity of the partial derivative with respect to alpha, okay, of t times natural log of t cubed plus alpha, okay, and then all of that is going to be subtracted by natural log. So this is in brackets, natural log minus natural log of t cubed, okay, and all of this is divided by t cubed plus 1. So this is just so that we can make it easier to differentiate, but it really does not make a big difference, right? It's just to get a clearer picture. So over here, the derivative with respect to alpha of this goes to 0, right? Because it's just a constant. So in this case, we consider that to be a constant. And so when we take the derivative with respect to alpha over here, we get nothing but, okay, so I prime of alpha is equal to the integral from 0 to infinity of t multiplied by 1, right? Because the derivative of alpha over here is 1 and the derivative of t cubed is 0 with respect to alpha, okay, and then all of that divided by this part over here using the chain rule, t cubed plus alpha, okay, multiply that by dt, okay, and then over here we have t cubed plus 1 on the bottom. So as you can see, this can be much easier to visualize. We don't have any natural logs anymore. So now from this, what we do is we try to somehow integrate this in terms of t. Okay, now we're going back to the t world in such a way that we can go back to I, but in a much smoother way. and we're going to have some algebraic expression in terms of alpha and t. So once we plug in our limits from 0 to infinity, you only get an algebraic expression in terms of alpha. We know that for our original integral, alpha is equal to 1, so if we let that equal to 1, we will see what the actual value of this integral is. Of course, we have to look at several cases in order to find the balance of integration. Once we finish this, once you integrate this in terms of t, you have to integrate it in terms of alpha. So it's a double integral, okay? So, but now for this part, we're only going to find, okay, a better expression for this. We're going to integrate this in terms of t, and we're going to get something in terms of alpha, okay? All right, so for this now, what we're going to do is, because we got this over here, the next step will be to make a substitution, okay? So in order to integrate this, because we don't really have, some way to, separate this using partial fraction decomposition, then the next step will be to make some, substitution over here in such a way that we can, decompose this using partial fraction decomposition. So for simplicity, let x, right? Let x equal to t cubed, okay? So that x is going to be t cubed, which means that t is going to be x to the 1/3. Therefore, if we want to find dt, it's nothing but 1/3 of x to the 2/3 on the bottom times dx, okay? So this is going to be important in order to substitute, and so we can make our substitution. So let's see, we get that I prime of alpha is equal to integral from 0 to infinity of t, but t is x to the 1/3 times dt, which is nothing but 1/3 times x to the 2/3 dx on top. And on the bottom we have t cubed, which is going to be in this case x plus alpha times x plus 1. Okay, so this is going to be the new integral after the substitution. Over here we can simplify this. We have 1/3 of the x here, and then we have another third, so we end up with 1/3 outside of the integral from 0 to infinity of dx divided by x to the 1/3 times x plus alpha times x plus 1. All right? Okay, so now we're going to use partial fraction decomposition, but it's going to be a special way to do it. So we're going to let this equal to, so this integrand over here, we're going to call it integrand, little I, so I lowercase, and we're going to call little I a divided by x to the 1/3 multiplied by x plus alpha, okay? And that's going to be our a, and then b, okay, so plus b is going to have x to the 1/3 on the bottom multiplied by x plus 1. So this is going to be our partial fraction decomposition, our first partial fraction decomposition, because most of this integral has to do with partial fraction decompositions. So that's the basic building block. Okay, so this is the most fundamental method for this integral. Okay, so now in this case we say that this expression will be equal to dx, which is 1. So in this case it's going to be 1. Let's not forget that 1/3 outside, so let's just leave that 1/3 outside and let's see what happens. Okay, so we find the least common denominator for this fraction. So we multiply by x plus 1 over here, and then we multiply by x plus alpha over here. Okay, so in that case, we know that this over here has this same common denominator, x to the 1/3 times x plus alpha times x plus 1. And so if we do the same thing on the bottom, so this over here has to be multiplied by x plus alpha okay? And this over here has to be multiplied by, I'm sorry, the other way around. This has to be x plus 1, and this has to be x plus alpha. Okay. So in that case, this cancels out, okay, with each of them, the denominators cancels out, so we end up with a times x plus 1 plus b times x plus alpha, okay, equals to 1. So in that case, we can let x, for our convenience, equal to -1, so that this term goes to 0. In that case, we know that if x is -1, then b must be equal to 1 over alpha minus 1, okay? So that's b. And now we can also let x equal to -alpha. So if x equals -alpha, what's going to happen is that this term goes to 0, and so if we put -alpha over here, we know that a is going to be -1 divided by alpha minus 1, okay? So it's just the negative of b. In that case, what we can do is we can rearrange this whole expression. So we have that I prime of alpha is going to be 1/3 of the integral from 0 to infinity of a, which in this case we found was -1. Okay, so let's put b first and then a afterwards. So b is 1 over alpha minus 1, okay, on the bottom. And of course we also have x to the 1/3 multiplied by x plus alpha, okay? That was x plus 1. Yeah, that was the original one. And that's going to be subtracted by b, which is 1 over alpha minus 1. Okay, all of that is going to be multiplied by x to the 1/3 and x plus alpha. So x to the 1/3 over here, and then we have x plus alpha. All of this is going to be multiplied by dx. Okay? All right. So now that we have this, we can factor out this constant. Okay, we can consider alpha to be a constant for now. So we have that I prime of alpha. Let me write alpha in black, in red. So okay, so that's going to be 1/3 times alpha minus 1, okay, times the integral from 0 to infinity of 1 over x to the 1/3 times x plus 1 minus 1 over x to the 1/3 times x plus alpha. And all of that multiplied by dx. So this is what comes out of that. Okay, so what we can do next is basically another substitution over here. But in order to do that, let's think about these two parts of the integrand. If you can observe these two parts of the integrand as very similar, very similar. If you let alpha equal to 1, this whole integrand is equal to 0, right? So let's solve for this general case to find the same integral for this over here. So we don't have to do it twice, right? So this over here is what we're going to solve for. We're going to call it I1. So I1, okay, in this case, let me use another color now. Okay. So I1 will be the negative. Let's forget about the negative for now. We know we have a negative. So it's just the integral from 0 to infinity of 1 over x to the 1/3 times x plus alpha dx. Okay? Now for this integral, let some other variable, so let, for example, omega, okay, let omega be equal to x to the 1/3. Okay, x to the 1/3 will be omega, and we know that therefore x is equal to omega cubed, so that means that dx is equal to 3 omega squared d omega. Okay, In that case, we can substitute this whole system into our integrand, and we get that I1 is equal to the integral from 0 to infinity of dx, which is nothing but 3 omega squared d omega divided by x to the 1/3, which we said was going to be omega, multiplied by omega's cubed plus alpha. We cancel out 1 omega on top and bottom, okay? And then we're left with 3 times the integral from 0 to infinity of d omega times omega. So let's put omega times d omega divided by omega cubed plus alpha. So this is the integral we're going to solve now, and it's a very common integral for this problem. We're going to find it several times, so that's why I'm going to solve it once only. So then from here, we have that I1 is equal to 3 times the integral from 0 to infinity of omega d omega divided by omega cubed plus alpha. And so this can be trivially solved by expanding the bottom as a factor of the sum of 2 cubes. Okay, so because over here we can show this to be I1, okay, divided is equal to 3 times integral from 0 to infinity of omega d omega, and then divided by the factorization of the sum of 2 cubes. And if you remember over here, we have, of course, omega is going to be cubed, and then the cubed root of alpha is going to be cubed. So we have the sum of 2 cubes, and this can be factorized, okay, as the following. So this is nothing but omega plus the cube root of alpha, okay. All of this is going to be multiplied by omega squared minus the cube root of alpha times omega plus alpha to the power of 2/3. So this is going to be the integral. This can be trivially done, okay, by using, again, partial fraction decomposition. But, so for this case, we're going to do the same thing, right? So let's see, we have now that I1 is equal to 3 times integral, but let me first do the partial fraction decomposition. So that means that, let's say that we have the integrand over here, okay, little I, is going to be nothing but A, so let's call it A, divided by omega plus the cube root of alpha, and then plus B times omega plus C divided by this whole expression, which is omega squared minus the cube root of alpha times omega plus alpha to the power of 2/3. Okay, and all of that we can set it equal to, we can bring the 3 into the integrand, so let's say it's going to be 3 times omega and divided by the common denominator. So we find the least common denominator over here, and we get that A times omega squared minus the cube root of alpha times omega plus alpha to the power of 2/3, okay, and then we're going to add B times omega plus C multiplied by omega plus the cube root of alpha, okay, and all of that is going to be equal to 3 omega. Okay, so now in this case we do the commonly done thing, which is to expand this as a polynomial, or at least what we think it could be a polynomial in terms of alpha, omega. So we're going to have 1a squared times 1a times omega squared, right? So we're going to find all the numbers that add up as a factor of omega squared. So in that case we have a plus, okay, where else can we find that omega squared? So b omega times omega gives us omega squared, so we're going to have a plus b. And we also have, that's it, so that's it for omega squared, so omega squared times a plus b, plus, now let's look for all the factors that add up to omega. So we got a times negative of cube root of alpha. So we got negative a times the cube root of alpha. Okay, what else do we have? We have b omega times the cube root of alpha. So we got plus b times the cube root of alpha. And we also have c times omega. So that's plus c. Okay, and then all of that multiplied by omega. Now, finally, we have a times omega, a times alpha to the 2/3. So we have plus a alpha to the 2/3 multiplied by c times the cube root of alpha. So we have plus c times alpha to the 1/3. All of this equals to 3 omega. Now, we know that a plus b, okay, a plus b is going to be equal to 0. And this whole expression over here will be equal to 3, right? Because this is a factor of omega. And this whole expression over here will be equal to 0. Okay, so from this, we can easily solve everything in terms of a. So let's say that over here b is equal to minus a. And over here we have, because this is equal to 0, we cancel out 1 alpha to the 1/3. Okay, so we get that c is equal to negative a times alpha to the 1/3. Okay, so that's going to be everything in terms of a. So we plug that into this equation over here, which is equal to 3. And so we get that negative a times alpha to the 1/3 plus b, which is negative a. So we're going to give minus a times alpha to the 1/3 plus c, which is minus alpha. Minus a times alpha to the 1/3. So all of these are the same. That's equal to 3. And so we have 3 of the same. 3 cancels out. So we get that a is nothing but minus 1 over alpha to the 1/3. So this is a. Now let's find what b is. So b over here is going to be minus the negative of a, which is nothing but 1 over alpha to the 1/3. And c, finally, is going to be negative a. Okay, so it's going to be negative a times alpha to the 1/3. So it's nothing but positive 1. Okay, so we got this and that, and we plug that into this over here. We integrate it from 0 to infinity times d alpha. Times d omega, and yeah, we can solve this. We can solve this pretty easily. Okay, so now that we have the new I1, okay, which is part of the integral of this over here, which is I prime of alpha, we're going to get that it's nothing but 1 over alpha to the 1/3 of the integral from 0 to infinity of minus 1 over omega plus alpha to the 1/3 plus omega plus alpha to the 1/3 divided by this. And this over here has a special way of solving it. So we're going to take a look at that. This one is trivial to integrate. That's nothing but natural log of the bottom. So we have that then I1, okay, I1 is going to be nothing but 1 divided by alpha to the 1/3, okay, times the integral from 0 to infinity of this over here, which is going to be omega plus alpha to the 1/3 divided by omega squared minus alpha to the 1/3 omega plus alpha to the 2/3 d omega. And this over here, we know that it's going to be nothing but minus not the 1 over alpha to the 1/3, okay, times natural logarithm of absolute value of omega plus alpha to the 1/3, okay? And of course, don't forget to evaluate this from 0 to infinity. It doesn't matter that the limits are in terms of x, because remember that initially we said that omega, okay, was going to be equal to x to the 1/3. So the same limits apply for this integral, just like the one from before, so before the substitution. And now for this integral over here, which is a special one, what we can do is we can split this into two integrals. Again, right? But now one of them will be easy to solve. The other one is just a trigonometric substitution problem. So in that case, we're going to take advantage of the bottom and its derivative. So we're going to take the derivative d over d omega of the denominator, which is omega squared minus alpha to the 1/3 times omega, okay, plus alpha to the 2/3. And that's nothing but, okay, 2 times omega, then minus alpha to the 1/3. This over here is the key to solve this easily, because if we somehow take advantage of that and make the numerator equal to this derivative, then we can use U-Substitution. We can use any substitution really, and then we can make it easy to solve. So let's see. How do we do this? Well, it was not easy to find how to do it. In the end, I think I had to even use Wolfram alpha, but for this specific part. So let's see. For that case, we know that I1 is nothing but 1 over alpha to the 1/3 multiplied by the integral, okay, from 0 to infinity. And then what we're going to do is we're going to multiply the top and bottom by 2. So we're going to do that, multiply the top and bottom by 2. So on the bottom we have the original, omega squared minus alpha to the 1/3 times omega plus alpha to the 2/3, okay? And then on the top, what we're going to do is we're going to have omega, okay? And what we'll do next is we're going to make sure that we have negative omega, okay, over here. So let's just see what's going to happen. So over here we're going to have plus omega to plus alpha to the 1/3, right? We want to make sure it's minus alpha to the 1/3 so that it matches with the derivative. So if we just add it over here as the original, alpha to the 1/3, what we can do is, so overall we're going to have 2 omega plus 2 alpha to the 1/3. We want to split this in such a way that we have minus alpha to the 1/3, and we don't change anything. So what we do is we subtract an alpha to the 1/3, and we have to add it back. So plus alpha to the 1/3, all of this d omega. So this over here, and this becomes 3 alpha to the 1/3, and we have the derivative over here. Okay, so we only care about this part and this part because that's the result of the derivative. And that's what's left is going to be 3 alpha to the 1/3, and that's going to be the other integral. So overall, what we're going to have is I1 is nothing but 1 over alpha to the 1/3 times the integral of that, which will be nothing but 1/2. Okay, so let's put the 2 over here. 2 times the natural logarithm of the absolute value of omega squared minus alpha to the 1/3 times omega plus omega to the 2/3 in absolute value. Okay, and then the other integral is going to be like this. It's going to be plus 1 over alpha to the 1/3 times the integral from 0 to infinity, okay, of 3 times alpha to the 1/3, right, divided by 2 times omega squared minus alpha to the 1/3 times omega plus alpha to the 2/3, okay, d omega. So what we have now is that we can cancel out an alpha to the 1/3, and then what we have to do is complete the square on the bottom. So we complete the square on the bottom, and then we can do some trigonometric substitution. So essentially what we can do here, okay, so let's call this new integral I2. So this is going to be I2. So I2, for I2 what we're going to do is we're going to complete the square over here, and in order to do that we have to take this over here divided by 2 and then square it, right? So basically what we're going to do is we're going to add alpha to the 2/3 divided by 4, and then we're going to subtract that again. We have to subtract it so that we don't change the whole expression. Minus alpha to the 2/3 divided by 4, right? So then we combine this later, and we see what happens. Now, once we get that, we take the 3/2 out of the integral to make things easier and more visualized. And so what we want to do is we're going to let, let me just do the whole thing. So we have I2 is equal to the integral, okay, so we have 3/2 times the integral from 0 to infinity of d omega divided by omega minus omega to the, so we have omega minus alpha to the 1/3 divided by 2. All of this is going to be squared. And of course, if we add what is left, which is alpha to the 2/3 minus alpha to the 2/3 over 4, we get 3/4 of alpha to the 2/3. So we have plus 3/4 alpha to the 2/3. So in that case, we can use trig sub. This looks like tangent squared plus 1, which is secant squared of theta. And so we're going to make the substitution, okay? Omega minus alpha to the 1/3 divided by 2 is nothing but tangent of theta, but we have to multiply by the square root of this factor. So we have to multiply by the square root of 3 over 2 times alpha to the 1/3, okay? So that we make this easy to factor. Okay, so from this substitution, we know that omega minus alpha to the 2/3, to the 1/3 over 2 is equal to radical 3 over 2 times alpha to the 1/3 times tangent of theta. When you square both sides, you can bring this to the bottom, and then you have tangent square theta plus 1. You can factor out 3/4 of alpha to the 2/3 out in the bottom, and you know that d omega is radical 3 over 2 times alpha to the 1/3 secant square theta d theta, because the derivative of tangent theta is secant square theta. You plug that in here, and then you have this nice trigonometric problem. This over here is nothing but secant square theta, okay? So this cancels out with this, okay? And this becomes 3/4. 3/4 cancels out with 3/4, okay? And 1/3, 1 alpha to the 1/3 cancels out with 1 alpha to the 1/3, okay? So then over here we are left with nothing but the integral of radical 3 of d theta, which is nothing but radical 3 theta. So if that's the case, okay, so this is nothing but radical 3 of theta from 0 to infinity. Whereas theta, if we solve for theta over here, we know that theta, okay, will be equal to arctangent of 2 over radical 3 times alpha, let me put it in red, times alpha to the 1/3 multiplied by omega minus alpha to the 1/3 over 2, okay? So that's theta. So then that means that I1, which is only this part of the integral of this, which is I prime of alpha. So this is, remember, I1, and we know I1 is that, okay? So we have that I1, finally, okay, if I1 is equal to, we can factor out 1 over alpha, okay, 1 over alpha. Remember this over here has alpha to the 1/3, okay? So we can factor out 1 over alpha to the 1/3 on all sides, right here, here. All terms have 1 over alpha to the 1/3. So 1 over alpha to the 1/3 multiplied by, okay, we can bring this together. So if we know that we have 1/2 over here, we bring the 1/2 as a power. So we have the square root of that. So we have natural logarithm of the absolute value of the square root of omega squared minus alpha to the 1/3, okay, times omega plus alpha to the 2/3 divided by, okay, because this has a negative, so you bring that to the power, and then it's to the power of -1, so it comes to the bottom. So we have omega plus alpha to the 1/3, okay, an absolute value. And so finally we add I2, and I2 is nothing but radical 3 multiplied by theta, which is arctangent okay, arctan of 2 over radical 3 times alpha to the 1/3 multiplied by omega minus alpha to the 1/3 over 2. So in that case, we can take the limits from 0 to infinity. It does not matter, because remember that we made the substitution that omega was going to be x to the 1/3, right? So if we said that the original limits were from 0 to infinity for the function evaluated at x, then it's the same thing for omega, so it doesn't matter. Now in that case, we want to take the limit, so now we want to do some limits over here. So we have 1 over alpha to the 1/3 multiplied by natural log, so we can bring the limit inside of the natural log. So this is going to be the limit as omega goes to infinity of the square root of omega squared minus alpha to the 1/3 times omega plus alpha to the 2/3 divided by omega plus alpha to the 1/3, okay, in absolute value. That's going to be one limit. Now we're also going to take the limit of this as it goes to infinity, so plus the limit of radical 3 arctangent of 2 over radical 3 times alpha to the 1/3 multiplied by omega minus alpha to the 1/3 divided by 2. Okay, and now in that case, as omega goes to infinity, what is going to happen is that this over here, we only look at the highest power inside of the radical. We take that power to the radical, so 2 over 2 is 1. We have the highest powers on the top and the bottom, the numerator and the denominator, which means that they're the same, and therefore the limit as omega approaches infinity of this expression will be nothing but 1. Okay, so ln of 1, natural log of 1 is 0. So this whole limit goes to 0. Okay, and now over here, let's see what happens. The limit as omega goes to infinity of radical 3 times arctangent of this whole thing. So let's look at omega. As omega goes to infinity, this whole thing explodes and goes to infinity. Arctangent of infinity is nothing but pi over 2. So therefore, we have that I1. So that's only for the upper limit, right? We have to evaluate at 0 as well. It's going to be 0 plus radical 3, okay? Radical 3 times pi over 2. So radical 3 pi over 2. And then minus, we substitute, and we evaluate the limit at 0. So natural log of 0, and then we get, don't forget that we have 1 over alpha to the 1/3 outside. So we have, and then minus natural log of absolute value of the square root of alpha to the 2/3 divided by alpha to the 1/3. And this goes to 0 as well, because this is nothing but 1. Natural log of 1 is 0. And now we finally subtract this arctangent, okay, radical 3 arctangent of 2 over radical 3 times alpha to the 1/3 multiplied by 0 minus, so minus alpha to the 1/3 divided by 2. This 2 cancels out with this alpha to the 1/3 cancels out with that, and the arctangent of 1 over radical 3 minus, right, minus 1 over radical 3. So if we look at the unit circle over here, it's going to be somewhere over here. So if we take the negative out, it's going to be somewhere over here, right? Because the cosine over here will be nothing but radical 3 over 2, and the sine will be 1/2. Therefore, 1/2 divided by radical 3 over 2 is nothing but 1 over radical 3. So arctangent will be 30 degrees, but we have negative, so it's minus 30 degrees. So it will be over here. Okay? So therefore, our final answer for I1, I'm going to write it, let me write it over here. Okay, so final answer for I1 is going to be, it's going to be 1 over alpha to the 1/3 multiplied by, okay, so in this case we have radical 3 pi over 2 And then over here we know that this is 30 degrees. 30 degrees is pi over 6, so radical 3 pi over 6. Minus radical 3 pi over 6. Okay, so that's it. And now we can factor out radical 3 pi. Okay, so we have nothing but radical 3 times pi divided by alpha to the 1/3 multiplied by this over here. We find the common denominator, common factor. So we have 3 minus 1 is 2. So we got 2 6 inside. This becomes 1/3. And this becomes, as a whole, becomes 2. It has to become, 2 pi. Okay, so it's going to be 2 pi divided by alpha to the 1/3, okay, times radical 3. This over here will be the answer to I1, okay? So if that's the case, what is going to happen, my apologies, over here we have a negative number, negative value, and because we bring the negative out, this becomes positive. So yeah, that's what happens, okay? So what happens is you're going to get 4, 6. And so that becomes 2 pi over alpha to the 1/3 radical 3. So this is going to be I1, right? But now, to find the entire expression, so to find I prime of alpha, we do the following. So we take advantage of what we just found. Okay, so what happens here is going to be like that. Okay, so because I1 is this over here, this only integral, what we want to do is we want to do the same thing for this over here, okay? So if alpha over here is 1, therefore that means that the final answer for I prime of alpha will be equal to 1/3 alpha minus 3 times the integral from 0 to infinity. Okay. Oh, I'm sorry, I already evaluated that. So it's going to be multiplied by, we found that this is the integral of that, so we put negative in front of it, and for this it's going to be the positive of that, where alpha is 1. So we got 2 pi divided by radical 3 minus 2 pi divided by alpha to the 1/3 times radical 3. Okay, so then from this, I will stop here and I'll make a video for part 2. But what follows after this is that you're going to have to take the integral again, because you have something in terms of alpha. So you want to know what is going to be I of alpha again. Okay, but now in this time is going to be in terms of one variable, and that's going to be alpha. So we want to take the integral of this whole thing, integral of I prime of alpha, d alpha. Okay, and you want to find the upper limits a and b, upper and lower limits at your discretion. So we want to make sure that it's in such a way that it's to your advantage. So that's it for now. This is part 1 of one of the examples of how to use Feynman's favorite integration technique. And I'll see you next time. So stay safe, stay home.